I'm here to talk about how you can engineer security into the development of a modern API system. There's an accompanying paper to this that was just recently published last week. So I invite you all you can go to the website on the SCI, on publications, and you can read the white paper, which goes into a lot more detail of what I'll talk about today. Kelly kind of ruined the beginning here for me. But yeah, so there's recently you probably could have noticed if you were going through airports, there were a lot of blue screens going on. This one was I found a little terrifying. This is an MRI machine with the blue screen of death in it. There have been cases where people undergoing cancer treatment had to stop because of the CrowdStrike bug. So, all this has had to do with APIs and a failure in being able to make systems secure and trustworthy for its users. So this is something that I'll come back later in this presentation. I'll first go over some important definitions for the rest of this presentation. Then I'll talk about the current state of APIs. I'll talk about how you can actually engineer security in APIs, and if we have some time, just a Q&A. So API stands for Application Programming Interface. I really like this definition from Joshua Block, who was the former head of Java at Google, where he says a set of functionalities independent of their implementation, allowing the implementation to vary without compromising the users of the component. So in other words, the system may change, but the interface it provides, its set of operations publicly available, doesn't change, if at all. So here's just kind of a diagram representation of this definition. Systems A and B have interfaces that expose a set of functionalities, operation 1, 2, etc., that they communicate each other via channel. These functionalities often have separate development rates of change than the systems that they provide functionalities access to. APIs are everywhere in software, from library components to classes and modules to the F-35 that I just showed you. For the purposes of this talk, I'm not going to go into real-time systems. Some of the things that I'll talk to do apply to them, but there's a lot of specifics to that I will go into. So for cybersecurity, cybersecurity is defined by the DoD as the prevention and protection from damage of electronic systems, such that it maintains the attributes of confidentiality, availability, integrity, non-repudiation, and authorization. Creating requirements for these qualities are part of the system's definition and analysis, and they are performed early and often as the system is refined or evolved. So like the polygonal fort that you see in this picture, security is very much dependent on the context in which it's being implemented. Back then, to defend against the new invention of artillery, nowadays towards more sophisticated attackers. So to engineer cybersecurity, I believe, is to come up with empirical, cost-effective techniques that maintain the system security attributes even in adverse conditions. If we're not empirical, that is, making decisions driven by data, then we're not really learning from our observations or those of others to create better solutions. If we're not creating cost-effective solutions, then we risk things being delivered over budget or not at all. And then maintaining security attributes comes down to the fundamental questions of how do you know that the system that you're creating is going to work as expected? How can you create a system that's trustworthy for its end users? These are the values that I believe are important in engineering security in APIs. And I'm going to mention a few principles and techniques that will help to realize some of these values. But let's talk about what's the state of modern APIs today. So modern APIs are, number one, ubiquitous. They are everywhere. They expose large amounts of systems functionality to users, and they require evolvable interfaces. That is, they require the ability to be both backwards and forwards compatible, all of which are different avenues that attackers can exploit. So APIs are ubiquitous. This is from a 2022 Landscape of APIs report from Cloudflare. It showed how most of the traffic on the internet is coming in from APIs, more than text or images, etc. Between 53 and 60% of all the internet requests were APIs. And they're also some of the fastest growing, it's the fastest kind of traffic on the internet nowadays. Alarmingly, they found that using some ML methods that about 30% more API endpoints exist than what organizations self-report. So, your organization probably has more APIs than what it thinks it has. And being able to recognize and identify those are extremely important. API usage is growing even in heavily regulated industries. So banking, telecommunications, they comprise some of the biggest growth in API usage. So if someone thinks that APIs can be used because they're inherently secure, well, there's a lot of these businesses that are putting themselves on the line because they realize the value that APIs deliver. So APIs aren't just used by internet companies, they're being used by everyone. And yes, including the government. So according to metrics collected by data.gov, there's been over 12 billion requests for APIs from the federal government. And there's over 300,000 unique API keys, which represent an approximate number of applications that are using some of this data to create different sorts of applications. So the second thing, so APIs expose large amounts of functionality to end users. So this is also from the Cloudflare report. Over half of the API requests are post requests, meaning that they are requests that modify the systems that the API is exposing. This includes adding an entry to a database, making a logical change, deleting resources, and so on. This represents an enormous amount of functionality that is being put out there on the internet for a clever attacker to abuse. Now, the importance of APIs to work as expected cannot be understated. One of the most famous cases of software failure was by the UK Post Office, where they, over the course of 16 years, they convicted and bankrupted hundreds of its own employees due to faulty accounting software that they were using for payroll. So the system regularly showed money disappearing from post office accounts due to bugs in the API. And I'm going to quote here from the news article, each time the user pressed enter on the frozen screen, it would silently update the record. In one instance, the bug created a 24,000 pound discrepancy, which the post office tried to hold the post office operator responsible for. So the post office never questioned the results of the APIs, and the result of that is that, a lot of these postmasters, many of which are elderly and poor, lost all their savings, sometimes were imprisoned, and their convictions were only overturned recently. The investigations are still ongoing. The lesson from this is that APIs have become an essential part of the workflow for many businesses and governments, and their behavior is usually taken as gospel. Users, either in the company using the API or either outside of it, should be able to provide rapid feedback to the API developers building the API to alert if something is going off. So the effects of faulty, these are some stats on the effects of faulty APIs. A 2023 Palo Alto Networks found that 92% of organizations surveyed experienced an API-related security incident. Of those, over half of them experienced multiple API-related security incidents, even though 3/4 of organizations reported having a robust API program. And separately, in a 2023 study by Akamai Security, 41% of their organizations had reported an API security incident. So there's some data to back up the case that there's a lot of work left to secure APIs. This is just a little comic. Hi, this is your son's school. We're having some computer trouble. Oh dear, did he break something? In a way. Did you really name your son Robert? Close parentheses, colon, drop, table students. Oh yes, little Bobby Tables, we call him. Well, we've lost this year's student records. I hope you're happy, and I hope you've learned to sanitize your database. So basically, this is a joke, but it comes down to APIs are at the forefront of security, and they need to be secured. Modern APIs require evolvable interfaces, and this was something that was said in some of the previous presentations, in which the rate of software changes very quickly. Now, some of this, it depends. Some of the older projects don't change as much as some of the newer ones. So for example, Linux and JIT, on average, every line of code changes every 6 years. Some of the newer libraries like Keras from TensorFlow, Angular, or Kubernetes, a line of code is expected to change once every 6 months. The median, which is taking account dozens of open source projects, is that every line of code is expected to change every 3 years. I'm sorry, it's half-life, so half of it would change. So this means that software is expected to be flexible because it's going to change. So we as software designers need to be able to provide the assurance that APIs can work as expected for its users, that they're trustworthy instead of vulnerable, they're an asset to your organization instead of a liability, and that they can create value instead of harm. For the rest of this presentation, I want to talk about how we can engineer our API systems in a data-driven, cost-effective way that maintain the system's attributes of CIA, as I just mentioned, even in adverse conditions. We want to engineer the security through continuous, rigorous testing that gives us a high degree of confidence that the system is easy to use. Sorry, it's safe to use. So since we're interested in building APIs quickly, of high quality and securely, our best methodology that we can use is DevSecOps. DevSecOps allows for empirical development techniques by reducing the number of variables being changed and deployed in a system. So instead of developing for 6 months and then having a big bang deployment, we make changes small, atomic, tested, and fully reversible. If a change causes a service failure or a bug in production, we can easily identify the root cause, roll it back, and redeploy. So I'm going to talk about each one of these stages. So let's talk about development here. So what you're seeing in there, it's a graphic on the dependencies between packages in a Linux Arch installation, which I thought is pretty cool. You can actually install it on your system, and it'll update every time you install a new package. You can clearly see the dependencies between these packages. And this is true for most software overall. So the OpenSSL library, which is ubiquitous because it's what allows you to communicate over HTTPS, it has 59 dependencies. The Debian operating system has over 170,000 precompiled dependencies. The effect of having some of the most popular software libraries depending on hundreds or thousands of other libraries creates a very large attack surface that an attacker can exploit. In fact, 84% of breaches have occurred in the application layer. So to counter this, we need to be able to have scanners that can check for known vulnerabilities in software packages or dependencies, and a software bill of materials for an accurate, detailed view of all the currently used software that our systems are being used. The SAA has done extensive research on some of these things like SBOM, so I encourage you to take a look at it. Now, the best time to scan for a package is the moment that it is requested. Some organizations scan weekly or at a monthly basis, but in DevSecOps model, security is performed the moment there is a change. So in this case, when it's first installed. There's artifact storage software, such as Artifactory or Amazon Inspector, that can scan packages when they're downloaded, and it can run periodic checks to ensure that there's no recently discovered exploits. There's also numerous vendors for scanners that exist that provide this whole bunch of scanning, which you can use depending on the context of software that you're developing. And there's a lot of that. It's pretty depressing how these small open source projects end up becoming pillars for the open source community. I think we're good with that. So I also want to talk about versioning. So the concern with versioning is that when you're scanning for every change, it suggests that you have a way to actually track every change. The specific practice for this in development is to version control everything. Your code, your configurations, even your documentations and manifests, everything except secrets and credentials. The point of this is to be able to have a snapshot of the entire system such that any change that's introduced into the system that could potentially change its security posture can be traced back without you having to go through extensive, laborious root cause analysis. Additionally, if every change is made small, then it will make it easier to test, roll back, and reason about. It would truly create a system that grows incrementally rather than exponentially. one of the practices of continuous delivery, which is closely related to DevOps, is that you're going to be deploying every change. And one of the effects of this is that you, as a developer, become nervous about making large changes that could break production. So you actually make commits smaller so that they can actually pass through all of the test suite and deploy. And that's exactly what the end goal of DevOps is trying to achieve, making changes small such that you can actually identify them and be able to produce better quality software faster. We can also engineer assurance into the AI by versioning the API separately from the system that it actually supports. So this is beneficial for developers, but it also has special relevance for its consumers. So on the one hand, you can have APIs that are changing every time that your system is changing, which can cause a difference in the response. And every time you do that, you're going to be breaking the contract that you have with the clients consuming that. This is going to cause a lot of annoyance by your consumers. It could even potentially affect their operations. So you don't really want to do that. On the other hand, you don't want to be so scared that you don't want to be changing anything in the API because it's going to affect somehow the operations downstream. So you want to be able to reach a middle point. And in one of my studies, I think a really good middle point there was done by the Stripe API. So Stripe have changed their interface about 6 times in a major way in the past 15 years. Stripe, for those who don't know, is a commercial payments processing company. They process over $1 trillion just last year. They're valued at $65 billion. So any change that they make is going to affect the global financial market. Now, they've talked about extensively about their APIs in their engineering blogs, so I'll just summarize here. So initially, their API was designed to handle just transactions in the United States. It was pretty famous because they sold themselves as being able to provide payments in just 7 lines of code. However, as they started to grow, they also wanted to support ACH. They also wanted to support Bitcoin and various other international payment methods. So over the years, it started to accumulate lots of state machines, endpoints, and flags for developers so that they can still work with the same interface. They got to a point where the cognitive load for developers was really high, and they needed to somehow re-engineer their interface. So their solution to this was to get together a Tiger team. They closed themselves in a conference room for about a month, not the whole time, just don't worry. And that's kind of like a picture of the drawings that they were making. They would invite subject matter experts to help them with that. And they created this new method over there on the right, which unified everything that what they were trying to achieve into a more simple method. So they called it payments intent and payments method. It was aimed to basically abstract everything that they were trying to make with payments while making it simple for developers to use. This was more complicated than the initial version that they were using in the beginning, but the whole point of it is that this allowed for much greater flexibility and forwards compatibility if there was any further additions they wanted to make. So I think the lessons here are that APIs should initially be small and focus on what it is that they're trying to do. As the use cases increase, communications with clients is essential in order to determine what it is that clients want. And this has a corollary, which is you should be able to know who the clients of your API are. If you don't, it's actually better to just lock them out. So doing that and then creating changes to the interfaces should allow for backwards compatibility, but even more importantly, allowing for forwards compatibility, so they can allow for future flexibility and future change. This is where a lot of concepts that and Martin Fowler, Dave Farley, and a lot of the other Agile practitioners have talked about when it comes to making code that has cohesion and modularity, and this is where you actually start to see it in action, and it becomes less abstract. So in the DevSecOps model, testing is not a one-time activity, it's a continuous process. Testing provides increased assurance that the API will work as expected, and there's different kinds of testing that you can do. You can do unit testing to test at the expression level, individual code expressions, integration testing to test in between code components or modules, and end-to-end testing to test the functionality of the entire application. This diagram here is from a blog post from Uber that shows how they gain confidence in their release as the change progresses down their pipeline. So because of the API's unique role in accepting input from X number of clients and then passing it over on to internal systems, it has to be really resilient to all different kinds of inputs. And you can try doing this with unit tests, but sometimes the input space can become extremely large. So for that, you can also use fuzz testers, which is a non-deterministic way to be able to rapidly discover and explore different kinds of inputs. I just kind of categorize here between deterministic and not deterministic. It's not so clear-cut, but it just kind of gives you a view of all the different kinds of testing that you can do, ranging from end-to-end integration accessibility to actually having a QA team. Yes, like even within DevSecOps, QA teams, manual testing, they do have a role in doing this. So yeah, I think that's what I'll talk about. I was also going to talk about contract tests, but my colleague Alex Vesey is going to talk about contract tests tomorrow, so I'm not going to steal his thunder here. I think a final point about testing that I'll make is that ideally, testing should be able to be done in the local workstation of the developer. This is because if they do it locally in the development machine, it's going to give them the fastest feedback on whether or not the change that they're making is going to work as they expect it will. As an example, Uber's API gateway is able to run 11,000 integration tests, and I think it takes only a couple minutes to run. So this is very possible to do. If your organization is very large, then it has a large test suite, then obviously you can offload that to the cloud and make that run in certain workloads. But otherwise, running tests locally is considered a best practice. So the point of all this testing is that if we create thorough, rigorous tests for every change that's introduced into the API, it's going to build an assurance case for us that the API is going to work as expected. Now, it doesn't guarantee that it will work as expected or that it's absolutely secure, but our test suite is going to be our argument in favor that it's going to be doing what we expect it to do. And that's going to be based on the threat model that we have of our API. The threat model can be explicitly stated in a requirements document, or it can be implicit in either the mind of the developer who's writing the code or the project manager overseeing the project, which is not ideal. So once a change is ready for deployment, we'd like to limit the blast radius in case something goes wrong. Canary deployments is a common way to deploy a change to a small subset of users. It helps us to be able to test whether a change is functioning as expected instead of just rolling out like CrowdStrike just did. Now, let's say that something does go wrong. Ideally, we would want our system to be able to recover as quickly as possible and return to its previous state. The only way to do this is if our changes are small enough and and doesn't have dependencies that doing so would break, our deployment again. There's different strategies for dealing with deployments that have dependencies. Feature flags is a very common one. But then I just wanted to mention that because it goes back to the practice of making small atomic commits that you can easily roll back in case something goes wrong. And thirdly, there's also the practice of monitoring and logging. So yes, we want to be able to log and monitor what's going on in production. But even more importantly, and I think this is something that's going to take us more towards the engineering side of things, is if we're able to monitor how our systems are doing in real time and be able to predict what's going to happen, say like CPU load is increasing once this change was introduced, then we can take certain actions to prevent something really bad from happening. So this takes us from the stance of reacting to disasters to actually preventing them by using accurate measuring and monitoring. So I'm going to talk about here this is a little bit, I don't think I have how much time do I have left? Okay. So I'm going to skip through this really quickly. I just want to talk about the interface security. So the way that in interface security for API systems, you could broadly break it down into configuration management and the runtime. So for runtime, this is something that was recently done by Uber with their API gateway. Instead of having each different departments deploying their own API systems, Conway's Law, anyone, you aggregate all endpoints into an API gateway so that you can centralize your authentication, your authorization, and your logging and monitoring. And you can also have a standard security baseline. And you can also use stress testing to assure that if there's any kind of rate limiting that your API needs to have, then that's going to be much easier to do. And finally, to be able to do configuration management of your code. So scanning not only applies to your code, but also to your configurations. Very famously, there was a bug in a configuration in Facebook that brought down a huge part of their networking. So being able to scan for configuration is also very important. And then finally, so the API system security. So this refers to all of the underlying infrastructure that supports APIs. So think of your routers, your VPNs, your load balancers. A lot of these low-level devices have a lot of software vulnerabilities. In a recent example, the hacker group Volt Typhoon, which is a Chinese hacker group, they were able to get into Netgear and Cisco routers that had reached the end of their end-of-life support. And by doing so, then they were able to infiltrate a network and be able to get into different critical infrastructure here in the United States. So being able to have an inventory of those low-level devices, being able to update their software regularly are some good first steps towards helping to resolve some of those. And so, which brings us back to the beginning. On July 19th at 4:09 UTC, CrowdStrike pushed an update which caused over 8 million Windows computers to crash. The fix required manual rebooting in safe mode to delete the troubled file. Lack of testing, inability to roll back the change, no canary deployments made this change devastating to users, and some of you have experienced this firsthand. So this was the debugger output of what actually happened. I'm just going to say that essentially it came down to, there was a pointer and it was addressing an invalid memory address. So this huge thing was caused by one of the oldest bugs in computing, which is a null pointer dereference. And this brings me to my last point, use memory safe languages. So there's Rust, there's Swift, there's Clojure, there's so many different programming languages out there. And for those who are hacking at the operating system level, there's options like Zig, Rust, and Mojo that provide C-level performance, but without having to do manual memory management. And that concludes my presentation. Thank you.